Hello and welcome back to Calculus 1. This is section 2.5 on limits at infinity. And this is different than infinite limits because now we are asking x to go to infinity and we are examining the results we get. So previous time we were having the limit answer, right? The result of a limit to be infinity. Now the form of the problem is limit x goes to either positive or negative infinity of f of x, which will give us either finite value L, one of the infinities, or does not exist. So you have these three options in the end. Now each one of these answers tells us something very important about the function, and these concepts obviously will be back heavily in differential equations. You can technically use it to analyze your answers in differential equations later on every single problem in that course. So limit of f of x as x goes to either positive or negative infinity. So I'm going to have, let's see, I'm going to have, and we can do again the example using our famous 1 over x function, right, with x going forever, y going forever. There we go. And if you consider what's happening here on this side, and I'm going to, let's go orange here, whatever, orange. If I circle here and I just write limit x goes to negative infinity of 1 over x is equal to 0. So we see that as x goes to negative infinity forever and ever and ever and ever, the answer is creeping up to 0. Now that's a 0 on y, which means y equals 0, right? Which is x-axis. So we see that there is a line that the function approaches, and infinity, that answer would be equal to 0, because that's where it goes. On the other side, green, let's say, we're going to have limit x approaches positive infinity of 1 over x, and we still get 0, because now it's dropping into the value 0 as we go to infinity. So this is what it means for the function to have finite limit, but it's limit at infinity, because both of these ends of the function go to infinity, one to negative, one to positive infinity. But they go on forever. And if you let them go on forever, they will settle, right? The y value will settle at 0 from both sides. Another example. So that this takes care of the first example here. We'll add more to it. But I want to talk about the second example now. And let's say you have your good old function e to the negative x as x. Well, let's just say f of x equals e to the x, because I want to draw that first. This would be your decay function, which means that the value is going to decay. It's going to lose its value, right? So it has some point there. That's 1 in this case. This value is 1, but you can have that to be something else. So now, if you take a look on the green end, we still have the same thing like before. The limit x goes to positive infinity of e to the negative x will be 0. So if you let that limit go on forever, right, you see that the value of the function always approaches the level y equals 0, and we said that the answer of the limit is always the y value of the function. Now in this case, it's not a finite value of the function. I mean, it is, but it's not, if we compute at a point, it's not. It's in the limit, it's the finite, because the limit goes to infinity. But the interesting thing happens on the orange side, and I should maybe circle it this way. So over here, as the limit x goes to negative infinity of e to the negative x, you are going to get positive infinity as the answer. And that takes care of the second case, right, that you can get an infinity in this case. So that's that, and we'll give the names and things to all of those. Finally, you can have our good old friend, trig function, sine or cosine, it doesn't matter. Y equal cosine x, how about that? And you know, hopefully, because you should have taken and passed with flying colors your pre-calc course for trig. This graph will start at 1 and then oscillate like this forever and do the same thing on the other side and go on forever. In this case, limit of cosine x as x goes to either positive or negative infinity, I really don't care, is going to be limit does not exist. Because infinity is not a finite point at which you can compute the value of cosine. And cosine is periodic function, which means that after a certain time it repeats itself exactly as it was before. So when you look at this graph, once you go to infinity, you really don't have a tool that would say, okay, so cosine stops and then this and that is the limit. No, simply it's going to oscillate into infinity, oscillate forever, and because it oscillates, well, it could be any number between -1 and 1 for an answer. And that's obviously something that we don't want, because you do not want the multiple answers to a same question. So we just, since we could have only one answer and they can't agree, then the limit doesn't exist, because again, all of those infinitely many points between -1 and 1 would like their shot, right, to be the answer, but none of them are, right? None of them are the answer, because this function oscillates, does not behave uniformly. But then you would say, and you will see this later on, I'm going to also introduce another function that would be eventually solution of the differential equation for the pendulum and stuff like that. So you set something in motion and then it eventually stops. So you should be familiar with some kind of a pendulum, right, that hangs off of the ceiling, and then you punch it, right, and it goes on the side, and then it swings back past its equilibrium point to the other side, and then when it goes back, it's going to go a little less, and then with the next pass, it's going to go less still, and so on, and it's going to keep going less and less and less of a swing until it stops. So the graph for something like that would be, so if this shows the distance d, which is the displacement of the object, and this is in time, when you punch something and it was, peaceful at 0, when you punch it, you dislocate that, and then it starts oscillating, but then it starts slowing down, and then eventually stops. So this is the distance covered, and as you can see, with every next bump, there is less distance covered before it switches the motion to go to the other right side. So this is called oscillation with dampening, and there is a formula for this, right? Distance is equal to e to the negative, let's put at. You can do sine or cosine depending on, your problem, but this would be actually the answer, and we understand this parabolic motion very well. And a lot of stuff in nature, right, would work this way, and then it would eventually stop. Now, obviously, the pendulum stops due to air resistance, due to gravity, right, and it can swing for a long time, but eventually it will slow down to the point where it won't be able to move further. So here is your limit at infinity here. And in this case, we can see that you would have a limit. Now, this is a tough limit to figure out if you don't know mathematics and stuff that we are going to talk about later. But solving this limit is anything unlike you have seen so far. So looking at the graph of the function, right, it's probably the best way to figure out that this limit is 0, because you see it die out on the right-hand side and become 0. Now, the proper mathematical way to solve this is actually surprisingly easy. You have a negative exponent that pushes the whole expression into denominator. So this becomes limit t goes to infinity of sine bt divided by e to the positive at now. And this top, because it's a sine function and the range of the sine function is -1 to 1, this value will always be smaller or equal than 1. So technically you are getting 1 over infinity, and that goes to 0. So that's it's a very easy argument to make, right, to solve. So you can say this is the same as the limit t goes to infinity of 1 over e to the at, which works out to be 0 because 1 over infinity goes to 0. Now, those of you that are not clear on this concept, there is a very easy way to understand the concept, because it's very important not to make the mistakes later on in calculus. We also have 1 over 0 goes to infinity. And this was the one we talked about last class, right? But now we have the one above. Now, what is this, right? How do we show, without going into rigorous mathematical proof and, writing a 200-page paper on it, what is the easy way to understand and see that 1 over infinity goes into 0? Well, you have division. And if you stop and think about what division means for 5 seconds, all of this becomes clear. If I have 1 divided by 2, that is literally a half, which means that the 1 unit, which is the top, so 1 unit, is cut into 2 parts, 2 equal parts. There we go. So that's what the meaning of 1/2 is. You had to take a 1 unit and you cut that unit into into two equal parts. But then if you think about the 1/4, it's taking the same unit and cuts it twice to make 4 parts. Now, if you compare the size of your resulting piece, right here, and this one, for instance, you see that the half is much bigger, well, twice as big as a quarter. So what's important to understand is that the result got smaller as the denominator became bigger, which is why Joker kills the bus driver, right? So the less of a cut, right, is more per person. So that movie is really mathematically very important. So 1 unit and then 4 equal parts. So now if I go and say, okay, how about 1 over 16? Well, that's just going to be this thing cut, right? And it looks like shredded, like when you go to pizza, when you eat pizza at the children's party and they give you that slim piece that literally does nothing. You can take a look at how large, right, one slice over here is, and you realize that Now you have a larger denominator, but the resulting size of the slice, the cut, is much smaller. So if you keep cutting something more and more and more and more and more, you are getting a smaller and smaller and smaller and smaller piece, right? And finally, when you reach the infinity, the whole thing just gone, right? Because you at that point you split all the atoms and quarks and subatomic particles, and there's nothing left at the infinity because you keep cutting forever and ever and ever, and the result is 0. So we learned this limit of 1 over x as x goes to any of the infinities is equal to 0, and that's going to be referenced many times in the future. And the explanation is very, very simple, right? The larger the denominator, the smaller the result. So if you make denominator infinite, result is 0. So now we would like to see what we use this for, these limits at infinity. And the first and one most important, I would say, application for this would be horizontal asymptotes. Horizontal asymptotes. So we define horizontal asymptote through the limit again, and then when you see a problem involving horizontal asymptote, you're supposed to do the limit, right? So horizontal asymptote, ha, is a horizontal line y equals a, y equals L, where the limit x goes to positive or negative infinity of f of x was L. So now, with this definition, I can go back to my introductory on like the first line I wrote in a lecture today, and just add here in parentheses, let's go blue, horizontal asymptote. So if we solve the limit at infinity, meaning x goes to positive or negative infinity, and if we get a whole number as the answer, then that is your equation, the line y equals a number, that is your equation for horizontal asymptote. All right, so now that we know that, we can try and see what we have for some of our problems. So if you think about it, the good old problem y equal e to the, let's say, negative x, you are going to have this function go down like this. And what do we see if we are to take the limit as x goes to positive infinity of e to the negative x? We clearly see 0 because the function drops down towards 0 as x goes to positive infinity. The left-hand side is a different story. The right-hand side, the positive x-axis, is where the limit will go to 0 in infinity. Now let's take a look at some of these limits that are given to you in the homework and the textbook, and see what we can work there. So, oh wow, they do actually give you this nice. So they start with problem 17, where they say limit theta goes to infinity of cosine theta over theta squared. There's nothing to simplify or do algebraically in this problem because you have a mixture of trigonometric functions and polynomials. And all of that is combined into a rational function because there is a division between the two. And now we can use the argument from before. Maybe I should write that in blood. Sine x and cosine x are bounded by 1. So there is the idea that sine theta is always smaller or equal than 1, and the same for cosine. We did see this earlier, but now, right, here it is official on the side. So this allows me to change my problem and replace that cosine with 1 because that's the most it can be. Right? I'm taking its extreme value. This problem, the numerator, the cosine theta, can at most, right, be 1. And now, when I take the limit, we have 1 divided by value squared. That's going to increase the values and so on. So we are getting our infinity there. No, what am I talking about? 0, not infinity. Oops, 0. So we're getting a 0 as we go out to infinity. Again, we are dividing 1 by infinity. So if you're dividing 1 by infinity, you are getting 0 there. Let's take a look at something else. Do you guys have any personal favorites over here? Pages 100 and 101.
Professor, can you hear me?
Yes.
How is theta? How do you know that theta is infinity?
Well, it says theta goes to infinity. That's the statement of the problem.
So that part is given.
Yeah, you're solving. This is what was given in the book, and then you were supposed to solve the problem. You were supposed to take the limit.
Gotcha.
All right, cool. So now let's take a look at other problems. You know what? Let's just go with 18 because it has some really cool stuff. So limit t goes to infinity of 5t squared plus t cosine t divided by t squared. We have to use properties of limits here to split this into 2 separate limits. I mean, we don't have to, but it's, I guess, the easiest way to go about this, to see most of the, good mathematical work that happens in the background. We have a fraction, and fractions are very easy to split. Just make sure you keep the common denominator. So 5t squared over t squared, and then big fat plus, that's this one. And then you have the limit t goes to infinity for t cosine t over t squared. Now these t squares would cancel. Over here, one of the t's will cancel. And what I have is the limit t goes to infinity of 5 plus limit t goes to infinity of cosine t over t.
I have a question.
Yes.
So do we?
Oh wait.
We always.
No, it's not supposed to be cosine. It's supposed to be sine. Yes. Go ahead.
So. No, you're good. So hold on 1 second. So we always have to put limit, correct? Like so it's limit 5t squared over t squared plus limit like that. So that's a must, correct?
All right. And to reinforce that, let me just ask you, do you always have to put this plus as you go to the next line? Right? You see how you carry? This is an operation, right? It's operation, and you apply that to a function whenever you simplify a function to the point where you don't have to use it anymore, right? So you use the limit. So now, when I say what is the limit of 5 is 5. And then I have plus, and over here, I know that my sign is always going to be less than 1, so I'm just going to quickly rewrite this as 1 over t. And now that's going to go to 0. So we have 5 plus 0 equals 5. So the answer to your question is yes, you have to write the limit in every step until you use it. Later on, same thing with integration, because you will do a whole bunch of algebra steps and then finally do the integration. You have to write these mathematical operations, well, operators, in every step until you get to use them. And it's a good practice. I mean, what if you just forget to, bring it back because you didn't write it for 10 steps, and then you forget about it, which means that you just did all of the algebra and all of the things that are not Calc1, and when it came to take the limit, you never did because you never put the limit down there and you forgot that you're supposed to do it. So it has to be written every time until it's used to get the answer.
Okay.
Cool.
Thank you.
You're welcome. Anything else? All right. So now, what did I find looking at this problem 18? Right? Looking at this problem 18, I found that there is horizontal asymptote at 5, and the function will bend around that y equal 5 horizontal line to give us the number 5 at infinities, creating what we call horizontal asymptote. Now, you can go to graphing software, let's say called Desmos or whatever else. Wolfram Alpha will work. I mean, technically anything for graphing will work. And you graph this function here, and you will see that that graph would be, the graph of the function will be stretching to wrap around line y equals to 5 as the numbers go to infinity. Unfortunately, I can't do it right now to show you that on the tablet because of the way it's set up, but I'm changing that for future lectures. Right now, I'm just going to go on my computer and see how well the Desmos graph looks like, just for the hell of it. But I am asking you guys to actually practice these things and verify your answers. So I'm just going to go with 5x squared, and then plus t plus x times sine x. There we go. All of that divided by x squared. Just wanted to see, and exactly what I hope to see. So we have this x and y coordinate system. 1, 2, 3, 4, 5. At 5, horizontal asymptote. And then we see that there is this oscillation that goes like this. But then it starts following the asymptote. Oh, actually, no. It oscillates around the 5, so it goes like this. But then eventually dies out. So here is your horizontal asymptote at y equals 5. Make sure you put y equal 5. If you put this, I promise you 0 points in my book. I am highly allergic to this, because this is not mathematical notation. This is garbage. Never write that. The lines, vertical asymptotes, x equals a number, and then horizontal asymptotes, y equals a number. So you need to write the proper notation so people who don't even speak English can still understand because it's the universal language in the world. Mathematics is the same in every country, regardless of their, whatever type of government they have, and where they are. This is the same in every country, and the same notation in every country. So it's a universal language between us. Notation has to be followed the same way like everywhere else. Now, let's take a look at the problem that has polynomials. So, are there any horizontal asymptote for the function? I could just pick literally any one of them. So here, 9x cubed plus x squared minus 5 divided by 3x to the 4 plus 4x squared. So now we would like to know if there are any horizontal asymptotes. Well, we learned the definition, and we know that we are supposed to, in this case, take the limit of this as x goes to infinity or negative infinity. So 9x cubed plus x squared minus 5 divided by 3x to the 4th plus 4x squared. I'm going to teach you now the method to solve these limits. It is you divide everywhere by the highest exponent, x raised to the highest exponent you have, which is in this case 4. So you're dividing everywhere by x to the 4. And that's the trick. Now we have limit, x goes to infinity, and we simplify everything, so I get 9 over x plus 1 over x squared minus 5 over x to the 4th divided by 3 plus 4 over x squared. So this was basic algebra, right? We just cancel the exponents there. And now each one of these is going to go to 0. Because again, remember, you have 9 cakes, and you are splitting that in infinitely many slices. There's no cake. The slice is a 0 size because you split that infinitely many times. So you already exhausted the, matter and all of that and went way beyond. Each one of these obviously is 0 because you are cutting the finite amount of pieces, in this case 9 or 1 or 5 or 4, right? So you're cutting the finite amount of pieces infinitely many times because that goes in where x is in the denominator, and all we're going to get is 0 over 3, which is 0. So the horizontal asymptote is at y equal 0, and y equals 0 is the x-axis, right? So this function will have the horizontal asymptote in there at y equals 0, which is x-axis. Okay, now you see that I am looking for horizontal asymptote, and the way I set up the problem was to take the limit. Why? Because I learned my definition for horizontal asymptote. It clearly says that if you're checking for horizontal asymptote, take the limit over here, and if that limit turns out to be a finite value, your answer, right, the line for horizontal is going to be y equals whatever number you got from the limit. So y equals L in this case. Questions, concerns, anything? I am going to ask you to work on one of these examples. And I'm going to actually put in one with a little twist over here, just to kind of point out things that can go wrong. So x goes to negative infinity, that doesn't matter. Here you have your 40 x to the fourth plus x squared plus 5x divided by square root of 64 x to the 8 plus x to the 6. So your job is to figure out which one of these is your highest exponent, divide everywhere by it, and then go from there. And as I said, there is a trap there, so be careful.
Mm-hmm.
Any answers?
I'm not sure if it's correct, but would it be 0?
0. So y equals 0 is one of the suggestions. I'm gonna go with 5 by looking at the problem. I'm gonna go with 5.
I just have a quick question.
Mm-hmm.
So when you divide everything by x to the fourth,
Mm-hmm.
are you able to divide the terms inside the square root as well, or?
Yes, because it's gonna go in as x to the 8 and distribute over both of these separately. So you have yes. So the reason why I asked this problem is because the most common mistake is to use x to the 8, but it's actually x to the 4th. Very good. So x to the 4th is the one that we divide everywhere, because square root of 8 is a 4 in this case. You cut it in half. So this one will be divided by x to the 4th. Now, we're going to go here and say limit x goes to negative infinity. And we're going to have our 40 plus 1 over x squared, and then plus 5 over x cubed, divided by, and here is the square root of 64 x to the 8 over x to the 8 plus x to the 6 over x to the 6. So when you are stuffing x's into the square root, you are actually doubling the power. And then when it's going out of the square root, you do the half of the power. So this now works out to be limit x goes to negative infinity, and you have your 40 plus 1 over x squared plus 5 over x cubed divided by square root of 64 plus 1 over x squared. And now when we apply the infinity, right, to each one of these x's in a limit, all of these go to 0. And you are left with 40 over square root of 64, which is 40 over 8, which is 5. So ha at y equals 5. Does this make sense now?
Yeah, pretty much.
Excellent.
So just actually, so if it's going into the square root, you would double it. But if it's going from the square root out, if that makes sense, you would take half of the exponent.
Mm-hmm.
So 4 to 8, and then it'd be 8 to 4, vice versa.
Yes.
Okay, perfect. Thank you.
You're welcome. All right, so we have our horizontal asymptotes. That's the story of the horizontal asymptote. You take the limit and you see where the limit goes, and that's it. Now the next part on our list is that part in the middle where we said that you can also get infinities. That is going to be labeled as end behavior, which is another thing you learned in pre-calculus course. End behavior of the function. And this literally means which way does the function bend as it goes to infinity, right? So we can have something like wee, like that. See, and this is some function f of x. So on the orange side, we're going to have the limit x goes to negative infinity because it's going all the way to the left of f of x, and it's going to give us positive infinity as the answer. So you see two infinities there, because this motion that it's kind of sideways can be broken straight up, positive infinity, and straight to the left, negative infinity. So these are your x's, these are your y's. Same thing happens on the green side, right? On the right, this motion can be broken into two basics, right? Positive infinity here, negative infinity here. There are x and your y. So I can write limit as x goes to positive infinity on this side of f of x is going to give me negative infinity. So end behavior literally just measures, you know, to which infinity, positive or negative, that would go as you go on. So that's the case. All right, so let's draw a little, like a map or a graph for this. So you can possibly have the function bend this way, this way, this way, or this way. So if you draw x squared, you are using these two. If you draw x cubed, right, you are using these two. If you draw square root of x, you are only using this one. So all of these are the only four that you can have, and they combine into 100% of the functions that you can draw. If you go with the exponential function, right, we know this is the horizontal on the left, but this side over here is this one. So any function, literally, this is your ln function, this side also here. So all of the functions you have ever learned, right, they might have one of these ends that go to infinity in some sense. So all I need to do now is to say that this one over here is described by the limit x goes to positive infinity of f of x, giving us positive infinity, and the one on the bottom is limit x goes to still positive infinity, because you are going to positive infinity on x, and the result is negative infinity because it's going down in this case. Same on the other side. Here we have limit x goes to negative infinity of f of x, going forever up. That's a plus infinity there. And limit x goes to negative infinity on the bottom of f of x to give you negative infinity going down. Now, in your pre-calculus course, you only drew the picture in black, and then you said, okay, it goes up and to the right and blah, blah, blah. But now with these limits, we actually understand which way these go. So we can do all of these things with mathematical rigor. Right now we can mathematically describe using the limit and know that at infinity it goes forever up or forever down. Those are the positive and negative infinities. And if it sits at the value, it's a horizontal asymptote. So now go back to the beginning of the lecture and we write next to the other one the end behavior. So I go here. This is, oops. So over here I say end behavior. And finally, the last one, we already talked about it, is the oscillation. That was, right, when you have does not exist, because here it is, right, this example here is the limit does not exist. You can see it there, because you do not settle to a value to call it horizontal asymptote, but you also don't shoot off to any of the infinities. So therefore, the problem is oscillating, and for that matter, it does not have a limit as you go to infinity, because it has to be a single value. There was a question earlier saying, can we have multiple values and a range of values to be the limit? And the answer is no, because limit computes the y value at the point, right? So only one y value, because we are dealing with functions, and every input can at most have one output to preserve the idea of the function. So that's that part. And we have solved a whole bunch of these problems. With that, we end this lecture on horizontal asymptotes and so on. We're going to take a break. When we come back, we will work on continuity, which is continuity is 2.6, and has a lot of good information and useful for your later calculus career. So we'll be back, I would say, at 4:25 or so, and switch to continuity.